So today we'll speak about our rocket family called Arguna and show you some results and movies and images of the last starting campaigns of these rockets. And I hope you will enjoy, because there are a lot of images and graphs and movies, not so much formulas as for the last talks. So, why do we do this? What's our motivation? Well, we want to test on suborbital flights. That is, we have some subsystems. We want to know if they work on a real rocket. So we use a smaller rocket to go up to the stratosphere or higher, and then look in microgravity environment and vibration and high acceleration if the system are ready to go for space. And then we are very interested in experiments in micro-G, as during the free fall time of this rocket, a few seconds to 20, 30, 40 seconds, there is nearly absolutely no gravity. So microgravity is called. And in this environment, we can do special experiments like chemical experiments, physical experiments of all kinds, and material science experiments. So, and of course, our goal with this family of rockets is to cross the Kármán line. In other words, to reach space, suborbitally, but to reach it. So 80 kilometers plus. So the philosophy is keep it simple, stupid. We had some problems in the past with complex systems, and we thought, okay, one of our guys developed a solid rocket motor, and he had flown a lot of smaller rockets, and they're working just fine. So why don't just use it and get flying? So we used this solid rocket engine based on candy or on epoxy composite propellant, which he's an expert on, Ziggy. We'll see him later in the movie. And he's building rocket motors since, I don't know, 50 years or so. So he began as a very small child making black powder rockets, and then he developed a special candy, a so-called super candy, aluminum candy, and an epoxy composite that's very powerful, between 130 and 180 seconds. So we use common materials for our rockets. For example, the Arguna 2 here is mainly made out of wood, aluminum, and PVC plastics. So nothing exotic, no titanium, no beryllium, no whatever. So maybe the nozzle is made of graphite, but that's the most exotic material we use. And of course, it has to be simple to manufacture them. So the first Arguna rocket that we have not in display here wasn't built without even using a lathe. Okay, just a hammer, a saw, a drill, and of course a lot of sandpaper. And this leads, of course, to low budgets. For example, this rocket, the Arguna 2, will be in the range of €1 kilo in material, of course, a lot of time. And here, the Arguna 4, the larger rocket, will be about 2K in material and raw things that you need. But of course, you put in a lot of effort, and you use hundreds of hours of manpower that are totally for free, because we are just doing it for fun. And very important to us, the rockets should be reusable. So we have a recovery system, so they don't go ballistic and join the ground. It's about getting them back with the payload, if possible. So I'll show you just shortly what we did before we switched to solid rockets. We were mainly engaged in, I have no sound. Yeah. Louder, please. This is a hybrid rocket engine, and it's a very complex machine. And sometimes things go wrong. So we worked on these hybrid engines for about 7 years, and this was in 2001. And in 2004, we had a hybrid rocket engine that was working, and we were very proud of it and so on. But then we understood that it was very difficult to make this hybrid engine fly, because there were so many other subsystems that would be very heavy, and we saw that we would at least needed 3-4 years to even get flying. So when our guy Sigi came along, we said, okay, why not? And so we sat down and planned. I'll just show you a promotion video we made. It shows a workshop, how we sat down, thought about it, and planned this Arguna 4 rocket. So the Arguna 2 rocket was already done. Here you see this is in the Eifel. This is a radio telescope, the Stocker, that we will use in radio astronomy and radio amateur experiments. Oh, and during this workshop we designed the next rocket that is still not built, and this Arguna 4 rocket. So we thought about avionics, we thought about aerodynamics, about internal ballistics of the motor, and so on. So we sat down for about 3-4 days, and then we went away in all directions and started to plan and build the thing. The problem that we have as a community is that we are living in totally different parts of Germany. So myself, I come from the northern part of Germany. Here Hajo, he comes from the Eifel. The western part of Germany, we have some guys in Berlin, we have some guys in the south, at the Bodensee. We have some guys in Düsseldorf, in the Ruhrgebiet. So it's very difficult to get together, okay? So all our work is done over the internet, just like most hackers do. And then when we come together to discuss the things we have done. And the parts itself, we have a certain workshop in the Eifel too. They are designed at different places, produced there, and then integrated normally in the workshop. So this is from last year in Manching. This is in southern part of Bavaria, where we can fly on a small field near an airport to about 2 kilometers. So during the campaign, we just assemble everything on site. It's very simple, just making, as you see. This is Siggy, by the way. He lost a finger with some of the experiments, so you can see the finger, yeah? Okay. So this is the Arguna 1, and you have to be, this is very modular, so you have to build everything on site, because you cannot transport it easily when it is built, yeah? Because the pins are very fragile. You could, well, make something, nick it or so we assemble everything on site. Of course, the electronics is also assembled on site and tested just before launch. And for this event, we introduced some new features to the rockets, mainly HD cameras, because we were very unsatisfied with the movies we got from the former campaigns. So now they're making a hole for the camera. And this is the avionics section, so a lot of wires and connectors, it's a mess. We have improved a lot of that, so this Arguna 4 is much more modular than the former ones. The telemetry module, for example. Yeah, the transmitter. And this is our payload with electronics. You can see that we are still working on site. So it's really not like coming together and just launch a rocket. It's really work, and it's a lot of fun. So, and after everything is done, and the rocket is mounted, then we have to bring it to the launch pad. Well, this can take a while. This, by the way, is the largest rocket. We will discuss them in detail. This is the Arguna 3 that had a special sensor, a so-called optical horizon. You see here the opening for the optical horizon, and here the opening for the camera. And this optical horizon can give in-flight data about the attitude of the rocket during flight in relation to the horizon. The rockets are not very heavy. They are about 25 kilograms, so 2 men can just lift them without problem. Yes? Even with fuel on, because we have only about 3 to 4 kilograms of fuel in each rocket, because we cannot go very high. As I said, we have a series for 2 kilometers, no more. So we have to build very small motors. So this one here is the motor, and it's inside the house. So the motor is not as big as the rocket itself. This is different with the Arguna 4 because this was designed to reach very high altitudes. What you can see here are the pyrotechnic charges that will be used to eject the parachutes. And this little small mirror here is for the camera, so it can look down while flying. So we have a camera mounted on this position, and it will look outwards and downwards. So these are the preparations for launch. And there's an extensive checklist that we have to follow. And this is such a launch. It's the Arguna 3, and it just goes on. And this is the view from the inner HD sample. Okay, I was sure that you will see the movies later on in its full beauty. Okay. So about the rocket. Our first Arguna rocket, it was based on a previous rocket called Vision 3 that was very similar to this rocket and had 2 video cameras on board for stereo vision. But this rocket here was specially designed to have payload capacity. So this one can carry about 1.5 kilograms of payload in its bay, and it has less than 3 meters. Diameter of the rocket is 16 centimeters, so it's not very, very large. Lift-off mass, as I said, 25 kilograms. The payload. The motor has a total impulse of about 4 kilonewton seconds, and it produces a thrust of about 300 kilopounds. So it doesn't reach very, very high velocity, about 150 meters per second. This is 0.4 Mach. But the acceleration is large, so it takes off with about 12 G, and it reaches a peak height of 1 kilometer in about 14 seconds. And of course, the parachute's then open, so it descends slowly, and after about 2 minutes, it lands. And this is an image of the first maiden flight in 2005. So since then, it has flown about 6 times, I think. And this is the Arguna 2, you can see here on display. So it's slightly larger than the previous model. And the main difference is that it has been made with a much smaller diameter. It has only 11 centimeters in diameter. This is like it's very, very small, like a needle. And the intention was to reduce the air drag. So in this rocket, we can put in 3 different motors, a very small one for munching, a larger one, which will reach 2.5 kilometers and has been thoroughly used, as can be seen here in the specification, 2.5 kilometers. And we have a very large one that takes up half of the rocket, but we have never used it in practice, but we estimate that we could reach 5 kilometers with this motor, or 4.5 kilometers. So, just another image. So this is the Arguna 2 just after takeoff. The problem with this rocket is because it has a so low air resistance and a stronger motor, it accelerates at about 20 to 25 G. So it's difficult to follow it. And we will see that in the coming movies that people have problems following it. So this is the Arguna 3 you just see taking off. It's slightly shorter than the Arguna 2, but has a much larger diameter. This was made to accommodate more space for payload. So this one can grab about 5 kilograms of payload, and it gets nearly a little bit higher than the Arguna 1. But the point is here that we can accommodate larger payloads, like, for example, the optical horizon. Okay, and that's what you've just seen. So this is our new rocket you see here on display. The Arguna 4 is about a little bit more longer than 5 meters. It has a very similar diameter to the Arguna 2, a little bit larger, and it has a higher liftoff mass of about 50 kilograms. We can put a little bit more payload on it, 5 kilograms. So if you look at this rocket here, of course I cannot lift it. We have 2 payload sections. So this is the nose, here's payload inside, and this is the upper payload section. And we have here the recovery section. This goes until this coupler. And this is the lower payload section. So here is, this is a dummy antenna that we are using for testing. Here is a radio beacon inside, and the inertial navigation I will talk about in a few seconds, and some other experiments. And in the upper section, we have telemetry that relays GPS information and the information of the scientific payload. Yeah, so mal hochheben. Okay, you take it there. So just to show you. So at the moment, the motor is empty, so it's about 18 kilograms less weight, yeah, and you can lift it with 2 men. It's no problem. Yeah, no, it's okay. Vorsicht. Okay. So this rocket will hopefully fly in 1 month in Denmark at the northern shore, to be more specific, in Tranum. And if the weather is not appropriate, that happens sometimes in Denmark, then we have another launch window in October in Poland, in Drawsko-Pomorskie. And from our estimation, from our calculations, we'll reach something between 8 kilometers, depending on the elevation, to 10 kilometers. And it will be very fast. So it will reach nearly Mach 2, 1 point something, 1.7 or so. So this will be the first Arguna rocket that will breach Mach 1. Oh, by the way, the starting tower you can see here, it's 8 meters long. You surely wonder why use such a start tower for such a small rocket. The thing is that we are building another rocket, the Arguna 5, that will be slightly less large than this, but very much heavier. So we need a longer tower so the rocket can reach a velocity to be stable after clearing the tower. Okay, now I will show you some videos from our last campaign of these 3 rockets that have already flew. Let's start with, let's start with this one. This was in Bergen. This is in a training ground in the northern part of Germany. And this is a military place, so everything is burned and destroyed and full of ammunition. And we had a permit to launch there with the University of Bremen. And this is the Arguna 1, and it will go in this flight to about 900 meters. Sound, please. As you see, the flight is always very short, especially if there are any clouds in the way. So it's good to have telemetry, otherwise you don't know what is happening to the rocket. And on the same day, we had the launch of our Arguna 2 rocket. And we really didn't know how fast it would go. We just had calculated it because it was the first flight with the stronger motor. This is the so-called Suka candy, aluminum. You can see that the flame is not white, as is normal by candy, because normal candy is is not so hot. And Suka is much hotter, giving the flame a very orange-red glow. So it just So that's all you see of the rocket. You count to 3 or 2 and it's gone. And indeed, it was gone this day. So we didn't find it because it was very windy, and as we later found out, the upper section of the rocket did open both parachutes. We have 2 parachutes, one small drogue parachute that allows the rocket to fall very fast, and one larger main parachute that is, well, a problem if it opens up in such a height, because then due to winds, the rocket will move fastly away. And we didn't find it that day, and after we thought we had lost it. Yeah, we had a radio beacon on it, but on landing, the radio beacon just silenced, so we couldn't find it again. And then we had a call 4 weeks later from the Bundeswehr that someone had been wandering around, his dog had found a rocket. Okay, so we got our rocket back, but it was pure luck. Okay, so let's see then. Last year in Denmark, we launched again the Arguna 2, same configuration with Suka motor, and we told the people it will be very fast. And the military was watching us with a Doppler radar. And before us, there was some school kids. They were launching their small rockets all day long, and these rockets don't go out of sight. They were not very fast compared to Arguna. So everybody was expecting something like that. He even didn't react. So later on, the military came and asked, what was that? It was too fast for us. We couldn't track it. So then 1 month later, we flew the 3 rockets in Manching, in the southern, in Bavaria. And I'll just show you the preparations for the start and the launch itself, together with the new HD camera images that we attained during the flight. So these are the pyros. The pyros are a backup, a redundancy, because we want to have our rockets back, and it's common knowledge that parachutes tend to not to open if you have only one backup system, only one recovery system, because electronics can fail, especially due to acceleration and vibration. So we use a pyro to be absolutely sure that the parachute will open. So this is the plate, and you can see the plate is already quite demolished due to all the rocket motors working on it. And yeah, okay, just watch the launch. So in parallel you can see the images of the HD camera. And here's the airport. And it was a wonderful day with a blue sky, so it was very easy to follow the rocket because it only gets to about 1 kilometer shade, as you said. If you watch closely, okay, it's difficult. Now the parachute has opened, and when the rocket is hanging on the parachutes, it starts to moving very rapidly because it has no active attitude control. So the images, of course, are very moving too. And the darker, well, these are the woods. And on the other side, there is a lake or some lakes. So you really have to launch and land on this piece of grass, otherwise your rocket gets lost. Okay. So here you can see the launch site, still with smoke. This little thing that you saw was a test of a pyrotechnic device we will use on the Arguna 4. Okay, and this lake, very nice, if you don't fall into it. And touchdown. So that's how a good flight normally looks like. And we had 3 nice flights this day. I just show you the takeoff in slow motion, taken with the Casio EXF1, because it's so fast one normally doesn't see any details of the launch. Yeah, so as you can see, I think this is 300 frames per second or even more, 600. First the pyro goes off. This is the redundant pyro for the parachute. And then when we visually see, okay, pyro has ignited, then the motor is ignited, right just afterwards, manually. And when it does so, this rocket accelerates at about 11, 12 G. And when it leaves the ramp, it has about 120 kilometers per hour, increasing. So after 0.67 seconds, it has maximum thrust. Okay, we'll see that later. The other second rocket, the Arguna 2. This was, of course, not with the Suka motor, because then it would have been lost. We only can go to 2 kilometers, so this is the less large motor with a normal candy. And here the last preparation are done. This is the upper pyro, the lower pyro, and okay. Yeah, it's a very long rocket. So here below, Siggy is just preparing the igniter.
5, 4, 3, 2, 1, start!
So it's considerably slower as a Suka, it's not as difficult to follow, and with very nice images. These are the lake, this is the lake, and this is the part you don't want to land in. Smooth. This is microgravity now. It's falling. And then the sensors react, or the pyro, who's first. And then hopefully the parachute opens. like for example now. And once the parachute opens, it gets very ugly from a point of view. So I will just go a little bit forward because it is not a nice view. So we were very close to the lake this time. You can see sometimes still the smoke trail from the starting point. It's very, very bad contrast here, but you can see the lake out there, and if we had landed in the lake, the rocket would have been lost. So we landed instead in a cornfield, what was very simple to retrieve. Okay, after some walking, of course. Okay, and we knew where it had landed because we had always visible contact. So, and again, the flight with the Arguna 3 on this day. First, the slow-mo version of this flight taken with the Casio FX camera. Again, first the pyro up will ignite. You see the pyro burning, and then you ignite the main motor. And this rocket has about, I don't know, 180 kilometers per second when it leaves the ramp. Oh, okay, and it's gone. So, and the third rocket on this day was the Arguna 3. They had the optical horizon. And this one was Suka, because it's such a heavy rocket that you have to use Suka even to get to 8 or 1.3 kilometers. No, not due to the weight, due to the larger air resistance, because it's very, very large rocket in diameter. Okay, so just skip that part and go to the landing. Okay. Landing was very smooth. And we could just pick it up and use it again. Okay, that's what we call a smooth landing. Okay, you haven't seen what the Danish people do to the rockets. So to get back to our talk. We have, of course, payload on board. I talked yesterday about the avionics section. This is the old version of the inertial navigation, call it INA, and it has mainly 3 accelerometers. This is these black guys here. And we have 3 gyros on board. These are these evaluation boards, here 1, 2, 3. And 1 pressure sensor. So you can measure with this module the inertial observables acceleration, angular velocity, and additionally the pressure that gives us the height of the rocket above ground. So this is a payload of the Arguna 3, as you have just seen it fly. We had 2 data processing units on it with a propeller chip on it, and 1 GPS module, and the INA, and the so-called optical horizon. And this here is an improved version of the avionics you just saw. This is the Red Queen, and it's inside this rocket now. And we have these 2 sections, the lower section here that contains 1 data processing unit that gets the inertial observables from the improved INA module and stores this information on an SD card, and then streams the data upwards to the upper section here, through the recovery section. So there's a cable, an RS-232 interface leading up to this section here. And there is a second DPU, and this second DPU stores every information again on an SD card, just to be redundant. And it also measures 3 observables, the relative velocity with a frontal probe, the temperature with RTD, and the pressure, the ambient pressure with some pressure sensor. And connected to this CPU is the GPS unit, so it will relay over the telemetry the GPS coordinates once the parachute is deployed. So this is a view of the Red Queen GPU, as we can see them here. It's a very simple device. It's just a board 60 times 60 millimeters with one chip on it, and the rest is a lot of connectors and discrete stuff. So let's talk about results. This is from a flight of the Arguna 1. What you see here is a graph of the three acceleration components in 3 dimensions, x, y, z. So z is the red component, and at landing we have a very large acceleration, larger than during takeoff. So if you let something fall, you can actually get very high accelerations. So this is a zoom in of the first 25 seconds of the flight. So at 0 seconds, this is the ignition of the engine and liftoff. And you see that at the same time, you have a spike in the x direction and a little spike in y direction. This is due to the acceleration the rocket feels on the launch pad when going up the rail, okay? So then it leaves the rail at this moment, and the acceleration of the rocket motor goes up to 11, nearly 12 g, with a max acceleration at about 0.7 seconds, and it burns for 1.5 seconds longer. So after 2.3 seconds or so, the motor just shuts off, and no acceleration from the motor is measured. So instead, what we see is that the acceleration goes into the negative. Maybe the motor is a little bit chuffing, maybe it's noise, I don't know, vibration or so. And what we see here, the envelope, is the air resistance. Yeah, so negative acceleration due to air resistance. And then we enter 10 seconds into the flight into an area where we measure no acceleration, only noise. So we are in free fall for about, in this case, 4 seconds. Then at 14.7 seconds, we have a little jerk here. This is the ejection of the drogue chute. And the drogue chute expands 1 second later, and 4 or 5 seconds later, the main chute opens. And the rest of the flight is just hanging on the chute. So these are the angular rate sensors. And we see that here in front, they're very calm, no movement, then something occurs. It's a launch, the flight, zero gravity, and then the parachute opens, and it hangs on the parachute, and then it lands here. So to look at it in more detail, the red line is the angular velocity around the symmetry axis, so the rotation in this direction, direction of flight. And you see that right after launch, the angular velocity increases steadily until a point where it only decreases. And the other two components, they have a little jerk at the beginning when the rocket leaves the launch pad, but then they are very, very smooth. So the rocket flies stable. It doesn't move around, so it flies straight. But then after a while, it starts to tumble, and then when the parachute opens, it really moves around. So this is overlaid, the acceleration in that axis exerted by the motor, so the motor thrust, and you can clearly see that at the moment the motor shuts off, the rotation around the symmetry axis starts to fade. So the motor itself produces the torque to rotate the rocket during takeoff. And that's, of course, due to asymmetries during burn and asymmetrical mounting of the motor. Okay, so much for that. As an outlook, I want to present you the Arguna 5. It's based on the Aero-B design from the 50s. And it will be a slightly larger rocket than the Arguna 4, but much bigger in the sense that it has a larger diameter of about, I think, 27 centimeters. And the lower section here, the lower section is the whole motor. So the motor will contain about 200 kilograms of propellant. Not of Suka, because Suka is too brittle to be built in such large grains. There will be an epoxy composite that is much more stable. And we have two compartments, one for the recovery and the other one for the payload, and the nose cone will have also payload. So hopefully, next time we'll see us, I will report on this rocket. So that's all for now. Thank you.
You finished early. You surprised me. Are there any questions? Either from the floor or from the net? I believe we have a stand here even. Wow, God.
Does it work? Okay. I was just wondering, for the propellant, you call it candy. Is it actually sugar? And
Yes.
what is the oxidizer then?
Yeah, okay. It's actually sugar, that's why I call it candy. But there are a lot of sugars. Sugar is every polyalcohol. And there are people who use fructoses or glucoses, and we use sorbitol, which is a C5 sugar, and has a melting point of about 130, 140 degrees Celsius. And what you essentially do while producing the grains is you just take a pot, put the sugar in it, melt it over time, of course, using a thermometer, because if you heat sugar too much, it will caramelize. It's always a problem. And then we use sodium nitrate. Sodium nitrate as an oxidizer, but you could use, of course, use kalium nitrate or whatever oxidizer you want to choose. But nitrates, in our case, nitrates are very, very stable. Yeah, very stable. And we add some aluminum, if it's sugar, to boost the specific impulse. Okay.
Any more questions?
There's one. There's one.
Hi. Is there any active control? Are you moving the fins or thrust vectoring or anything, or is it just going straight up?
Yeah, at the moment it's only passively stabilized. We are thinking about it, especially the roll, because for the HD camera, it can take good pictures, but only if the rocket is really staying straight and not rotating. And as you have seen from the gyro sensor data output, due to the asymmetries in the thrust profile, you get always rotation about the Z axis. So it would be nice to start with a simple stabilizing algorithm that wouldn't impact the real flight of the rocket at the moment. So we have no active regulation at the moment, no control. It just flies passively.
Okay, there's one question from the IRC. Crocodilarian wants to know, when do you expect to reach low Earth orbit? And do you expect to be able to launch a satellite into that orbit?
Well, we have no time schedule at the moment, but we are thinking about it. So the Arguna 4 is a project to show that we can reach the stratosphere and get payload back. And the Arguna 5, the project I just mentioned, is a milestone to reach the space, but from there it is much more complicated to get into orbit. So we are thinking about it, but we need to use a stage rocket, and we have to use another technology for propulsion, because this solid rocket engines, they have specific impulses below 200 seconds, and that's not enough to reach orbit. But we're thinking about it. Ask me in 5 years. Okay.
We have plenty of time, so if you please want to ask questions, we have a good 15 minutes left. You have an expert here. Go grab him. Take a chance.
Cooperation between your group and the Copenhagen suborbitals, by the way?
No, sadly not. We tried. We had some contact, but they were so involved in their launching campaign this summer that they didn't want to be disturbed. So they just don't talk with you. Okay? But of course, we are interested in cooperation all the time, because there are so many synergies that could be used in cooperation. There's a cooperation with Danish Space Challenge in Denmark, and we launched together with them, and we tried to exchange technologies. But it's really, really difficult to join all the European amateur groups, because everyone is working alone and doing his stuff and not paying attention to what is happening in other countries and in other groups.
I do actually have a second question. I guess I could just look at the model here, but I was thinking, how do you actually eject the parachute? I guess you then split the rocket like the small ones, because that would probably do a huge bang when it opens.
Yeah, that's a good question. Okay, so this is the drogue chute from a drone, the CL289, if someone wants to check. It's a drone that lands by just ejecting this drogue chute from about 700 kilometers per hour, so it's very fast. It's a very heavy drone, so 200 kilogram or so. And what we do is we stuff this drogue chute in the upper part of the recovery section. So this section here is the drogue chute. And then up here, there is a CO2 capsule that is opened at the moment of recovery initiation. And then this front part here is movable. It is only held by two pins, by shearable pins made of nylon. And then it shears away by the gas pressure. That gas flows into the section onto the drogue chute. And then this here leaves off with a few meters per second, pulling out the drogue chute. And it opens, and the rocket hangs on the drogue chute for about 5 minutes, 4 minutes, depending on the temperature and so on. Yeah, sure. Just open it. If it doesn't, yeah, okay. So if you put 50 bars of CO2, it's much faster. Yes? Yeah. So, and then there is the main chute. The main chute is the largest part, so something like that. And when we reach about 300 meters, a second pyro fires, releases the main chute opens, and then it pulls out a buoy. Okay, because in Denmark we have to land on water, so we have to use something that helps the rocket to float, because it would just go under. It is too heavy to float by itself. Okay?
They all leave through the front.
Sorry?
The lines all leave through the front then.
The lines?
So it hangs on the tip of the rocket. The chute is attached at the front of the rocket.
The chute is attached at this point here, and there are shock bands leaving up to here, and of course the shock band has here extra protection, so it cannot be ripped apart if there's some bending. Okay? Yeah. So at the drogue chute, the GPS antenna is positioned. So with the drogue chute, the GPS antenna is pulled out, and then the rocket can get GPS information and telemetry relay to the ground station. That's the plan anyway. We'll see. Okay. By the way, please vote in the intranet on the talks. If you do so, don't complain about missing technical details, because now you have the chance to ask. So please ask if anything comes to mind. There are no dumb questions. Another question, very well.
When you showed the progress of your rockets, at one point you reached the speed of sound, as I understand?
Yes, this one will reach and go through the sound barrier.
So there's no, for me, there's no significant difference in the design of the rocket. I mean, for the airplanes, there's a significant difference in aerodynamics when you pass the speed of sound. It's for rocket, that's no special thing, or?
Oh yes, there is. Don't think that these two are very much related. They are very different in design. So this here is a full metal jacket, if you want so. This is made totally out of metal. It's very sturdy, it's very heavy compared to this one. It's made mainly out of very, very small aluminum and wooden parts and so on. So when you reach the sound barrier at Mach 1, then the problems begin, because the pressure point, it's wandering all the time, and there may be problems to it, and the drag, of course, increases dramatically, and it can happen that the fins disintegrate. So you have to look especially at the fin design. But of course, this rocket is very long. We have, we don't know if there will be any vibrations. We hope we have made it strong enough to survive it, because when you cross the sound barrier, there will be vibrations, no matter what. That's true, yeah. So this rocket is much more sturdier than the three former rockets. Okay? So.
5 more minutes if you want to ask anything else. guess it's my job to close this out. Can I thank you, sir?
Yes.
David Manila, FAR, for a truly amazing, wonderful talk. That was truly fascinating. And that's kind of it for the session. One last thing, a couple of things. If you do have any more questions, can we do it outside? Because we've got to set up for the next session. Do we have something online? Okay, just one more thing.
One more question. Have you thought about launching from a balloon to get to 50 kilometers and then to launch the rocket from there? Is that possible?
Oh, yes. The balloon thing. Out there are a lot of balloonies that think that launching from a balloon solves the problem to reach higher altitudes. Guess what? It's worse. It's worse. If you want to launch from a balloon, you have to build a balloon. Okay? That's normal. Then you have to fill it with something, like helium, for example, which is very expensive. So a filling of helium for a balloon to launch a very large rocket may be even more costly than the whole rocket itself. So instead of launching from a balloon, what we do is just build larger rockets, put more propellant inside. It's much cheaper because 1 kilogram of propellant may cost you 5 to 10 euros. And look up the price of helium, for example. Of course, you could choose another gas for the balloon or even use a hot air balloon. But if you make the calculations, it isn't worth it. It's just too much technical problems that arrive if you want to make something from a balloon. You have no control. You cannot go up with a balloon and fix something or check it or so. Everything has to go smooth. And every time someone tries to launch a rocket from a balloon, there are problems that would arise that are absolutely unnecessary, because when you launch from ground, there are no such problems. So we don't want to launch from balloons.
Okay, is there anybody else? Anybody else on the net? Good.
Another question.
I just thought of a thing, because I don't remember if you did talk about this in your hybrid rocket talk. Do you have some sort of, did you do any tests with a hybrid engine? Do you have any sort of preliminary design of some parts or even the whole engine?
Of a hybrid engine?
Yeah.
Well, yeah, we had a working design at the end, but the specific compass was very low because the burning efficiency was too low. Then we made some tests with paraffin and a diaphragm. So we positioned the diaphragm at different points in the burning chamber, and indeed the diaphragm increased the burning efficiency to a higher level. But since then we have not made any progress on that. But we are planning, after finishing the Arguna 5 project, which will be a very large solid rocket motor, then we will get to a point where increasing the solid propellant grains and increasing the fuel amount will really make things very difficult. Because if you have about, let's say these are about less than 20 kilograms of propellant. So you can transport it, and it's not very dangerous if you carry it around. But if you are producing it, it is dangerous. So you're producing something in a hot melt, because candy has to be produced in hot melt, so it's dangerous. So you don't want to produce very large quantities, just like 1 kilo or 2 in one batch. And when you produce composites, then you make it with polymers. But as we have seen, the specific impulse is not very encouraging, so around 130, 140, 150 or so, pushing in with aluminum, you can get to 160 or 70, but no more. So you have to change the oxidizer. You have to go to ammonium nitrate, for example, to get over 200. But then again, ammonium nitrate is much more volatile than sodium nitrate or something like that. Then it gets dangerous. Then you have, at the moment, you have a grain with 100 kilograms of propellant that is explosive, okay? And then you think about, oh, maybe I want to change the technology to something that cannot explode like hybrids. And that's what we are going to do. We're going to build now this rocket and show that we can go to space, and then we go back to the hybrids and build something large. And there are designs, especially by AMROC, and there are a lot of designs, and they are all open, so you can just read them and use them. And that's what we do. Okay? Another question from the IRC?
More from the IRC. What kind of official allowments are needed to launch such a rocket? Motor, free airspace, whatever?
Yes, this is very difficult. I'm not a specialist in this heuristic domain, but I followed very closely the problems that our guys that are specialized in this had. Well, in Germany, essentially nothing is possible except flying small model rockets. So this one is declared as a model rocket, okay? And okay, with the Arguna 4, it's getting quite complicated to define it as a model rocket. So what we did is we tried for about 5 years to get a permit to launch in a military space in Germany, and it was denied from us from the local authorities by several bogus reasons, as usual in Germany. But we have friends in Denmark and Poland and so on, and they just invited us, come over here, we can launch there. So in Denmark, there is an agreement between a group and the local authorities of the shooting ground, and in Poland, there's a similar agreement. So you can just go there if you have a rocket and launch to 10 kilometers. That's possible, okay? But if you want to go much higher than 10 kilometers, it's getting complicated. You have to go through the north of Europe, especially to Norway and Sweden, Kiruna and so on, and you can really buy for a day a launching ground where you can go up to 1,000 kilometers or so and test your rockets. But then you have to really be sure that it's worth a while, that you have a rocket that is working, a working design. Then you can go up to Northern Europe, okay?
Is everybody done? Well, I'll do that again. Thank you. Thank you. Thank you for a really amazing session.